Various inorganic fillers, such as calcium carbonate or talc, have been used extensively by the chemical industry in order to modify polymer properties to achieve certain goals. For instance, adding calcium carbonate to thermoplastics increases their cooling time, thus making them moldable for longer. In total, 75 million tons of fillers are used every year to make plastic composites for many applications, such as elastomers, adhesives, and sealants. However, traditional filler materials are not renewable or biodegradable, which raises concerns about their sustainability. Multiple sustainable alternatives have been proposed, such as starch, chitin, or natural fiber, and they have already been able to enhance polymer properties. Let's check them out.
When one thinks of starch, the last thing that comes to their mind is plastic. However, this popular ingredient is a promising polymer filler. Starches are polysaccharide carbohydrates comprised of chains of glucose monomers. These monomers each contain several hydroxyl groups, allowing them to function as both hydrogen bond donors and acceptors, as well as play an active role in polymerization. Starch can facilitate hydrogen bonding between nitrile rubber chains, enhancing the rubber's strength and extension at the point of breaking. It acts as a particularly effective additive by providing the necessary donor groups for interchain hydrogen bonding to occur. In the case of carboxylated butadiene rubber, starch can act as a cross-linking agent, binding the rubber chains chemically through ester bonds. Since ester bonds are by nature covalent, they provide much more strength to the polymer chains than electrostatic interactions such as hydrogen bonding would. As predicted, adding starch improves the structural properties of rubber significantly. Polybutadiene styrene rubber tensile strength increased upon the addition of polymethyl methacrylate grafted starch. In addition to this, due to its porous structure and ability to trap air, starch can improve polymer acoustic properties, allowing them to be used in many applications. Finally, being a preferred energy source of many microorganisms, starch additives improve the biodegradability of polymers.
Chitin is another promising biologically sourced filler. It is also a polysaccharide that often plays a structural role in arthropodal and insect exoskeletons and fungal cell walls. The N-acetylamine group increases backbone steric hindrance and therefore the backbone stiffness. It has similar reactivity and ability to be a hydrogen bond donor and acceptor as starch due to the presence of hydroxyl groups. In addition, its ability to form hydrogen bonds are facilitated through the amide group. The increased backbone stiffness of chitin has given chitin fibers an impressive elastic modulus of 150 gigapascals, which allows it to improve the structural properties of polymers more. Adding 3 weight percent chitin microfibers has raised the tensile strength of styrene butadiene rubber from 4.1 megapascals to 9.2 megapascals, a more than twofold increase. Chitin can be sustainably recovered from marine organic waste, and it's perfectly compatible with human bodies.
Even the things that we often see around us, such as wood, straw, and leaves, can be used as polymer fillers. This is partly due to lignin, a biological polymer, which greatly contributes to the rigidity of plant tissue. The presence of hydroxyl groups in the lignin monomers allow for hydrogen bonding with chains like starch and chitin. If a modifier is added, lignin is also capable of covalent bonding. One such modifier that enables strong polymer-wood attachment is maleic anhydride. This modifier has to be introduced before polymerization, and the subsequent esterification reaction produces a covalent attachment of wood to the polymer matrix. This enables interchain cross-linking via the wood particles. Blending natural fiber with various polymers has led to an improvement in the polymer structural properties. Adding 5 weight percent lignin to PVC increases tensile strength by 13.4%, and adding 4 weight percent wood flour to polyurethane both increases its tensile strength and nearly triples its elongation at break. All of these filler materials are abundant in nature, environmentally friendly, and safe for humans to use.
Overall, sustainable fillers have shown a good laboratory performance by improving mechanical properties of polymers through cross-linking or hydrogen bonding. Despite their apparent advantages, none of the mentioned fillers have found extensive commercial use due to a few reasons. First, the wettability of these fillers and their compatibility with polymer matrices are unsatisfactory for industrial applications. Second, traditional inorganic counterparts outperform sustainable fillers in terms of material property enhancement. Therefore, current and future research is focused on the interactions at the filler matrix interfaces to improve sustainable filler performance, thus making them commercially viable.